goodness. Should have done that before I deactivated the thing. Oh well. It is what it is. Boop. All right. Let me just check the audio. Yep, working. Excellent. Good morning, fancy meat computers. How is everybody doing today? Thank you for joining me on this Saturday morning. I hope that everybody is doing well. This is our long-awaited, much-anticipated makeup stream. So, let's get right into it, shall we? So, last time we were talking about factorial and all of the various ways that we can perform loop operations. Almost slept through class today. Yeah, you should have a kid. The kid will wake you up in the morning. Kids are the best alarm clocks, I think. There's no snooze button, you know? Anyway. So, we had talked about local variables. I remember, at the end of class last time, I went on an epic rant about global variables. So there you go. Yeah. So, factorial iteratively without multiple assignment. So, you know, you take this, you expand the, if you expand the multiple assignment in there, which I don't recommend you use anyway, this is what you end up with. All fine, well and good. We can also put multiple statements on the same line using semicolon. In most languages, semicolon is the end of line termination character. So this makes a certain degree of sense, but, you know, it's still not something I would recommend just because it's like non-standard. So here's an interesting variation, right? In all of these loops that we've looked at so far, we've started I at 0, and we have counted up to 1 less than n. In this example, we are starting at n and counting down. Right? Of course I am real streamer. What is this? Accusing me of not being real streamer in your head. Jeez. So, it turns out that the decision as to whether you want to count up or down with a loop is completely arbitrary. It works equally well, counting up as counting down. Now, of course, that's perhaps, you know, something specific to the factorial function itself. It actually only works because multiplication is a commutative operation. So A times B is the same as B times A, so it doesn't matter what order you perform the multiplications in. But yeah, so you can count up, you can count down, both work equally well. In this case, you can also modify the parameter that is being passed in directly. So this doesn't work in every language, but in Python, the arguments that you receive inside of a function are variables that you can use as variables inside of the function body. You can assign to them, you can do stuff with them. In this case, if we use n as the counter itself, we we can just sort of not have to worry about having an I at all, right? So this is useful to know because the modification of n inside of the function doesn't actually modify what you pass into it. So this is a pretty important result. Let me just pull up my terminal here. Python 3. Still getting used to this keyboard. Let's see. So let's just define a quick function. Function f takes n. N is equal to n times 10. Return n plus 50. Right? It doesn't do anything particular. It's just a numerical example, right? So if I set x equal to 9, for instance, and then I call this function on x, the result is 140. However, x's value has not changed. This n is not the same thing as the variable that we put into the function. They are separate and distinct. Basically, what's going on here is there's an implicit assignment going on between x and n. This is the way that Python works. It's called pass by assignment. So you may consider n to be a new variable, which is declared as the function is called, with the argument that's provided being assigned to n. So the semantics for this are the same as any other assignment, and we'll get into those sorts of things a bit later. Another thing that I want you guys to sort of absorb into your brains from this example, we have just shown you 5 different ways to encode the factorial function, which all work. There are many, many more ways that you could have encoded this function, right? In the same way when you're writing an essay, you make a large number of small arbitrary decisions about what word choice to use, how sentences should be structured, how to phrase things, that sort of thing. All of these tiny little decisions multiplied together mean that it's literally impossible for you to write the same essay as someone else, right? The same thing is true with programs, even reasonably simple ones, over, some, small number of lines of code. The approach that you take will be unique to you a lot of the time. So, when it's not, right, that's a pretty good indication to us that you've been cheating, right? In particular, certain internet sources, like Chegg specifically. If anybody uses Chegg, you should unsubscribe now. Don't give those fools any more of your money. They have a very particular way of going about solving problems, right? And it's like, again, the code that you write is as unique to you as an essay would be. So it's so dead obvious when someone's been copying off Chegg, right? It's dead obvious. So just write your own work and everything will be fine, right? So, good. So, one hazard that you might run into with this particular approach where you're modifying n, sometimes you run into situations where doing this can actually modify things outside of the function. So it kind of also gets into this problem of trying to make sure that function results are repeatable, which, is a good property to have, as previously explained. So generally, this isn't a recommended approach, but it's certainly possible. Any questions so far? Okay, good. So, I stated this last time in class, but let's go over it in the slides. All iterative implementations of factorial, at least the ones that we've seen here, use an auxiliary counter variable to keep track of how far along we are, and an accumulator variable, which becomes the result. Counting can go up or down, so up from the lower to the upper bound, or down from the upper to the lower bound, and the accumulator needs to be initialized to a value that is correct if the loop is not executed at all. This is a common error. So let's examine this one. Under what circumstances would the loop not run? This is a question to you, the audience. Under what conditions, for what input, would the loop not execute once? Anything below 1 or 0? Yes. Thank you, all you guys. So, if we get n as our result, or pardon me, if we get 0 passed into this function, let's just take a look at our definition and note that for n equals 0, we want the result to be 1, right? So, if this loop never executes, we are assigning f to 1 to f, and then we're just returning f. So there you go. It would be correct in this case. Right? Now, yes, very clever. So there you go. Another, error that you might have is if you initialize f to 0, everything multiplied by 0 is 0. So that would also defeat the purpose of the algorithm. So one thing that I want to, make plain to you, when you're writing an algorithm, there is no set of variables that you have to declare to solve a problem. There's no, I'm not trying to have you memorize, code blocks that serve, that's kind of, I kind of hate that when people do that. I remember, like, years ago, I was, I was tutoring someone who was, I asked them to program something in front of me because I was trying to help them be a better programmer. And, like, without even reading the question, they just open up a file and start typing. And, like, they're creating variables and creating loops and creating if statements. And I'm like, whoa, 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 whoa. You haven't even read the question yet. What are these all for? And they said something like, well, that's how you program. You have to make these variables. You have to make these loops. You have to make these if statements. And I'm like, not if the question doesn't call for them. You know? Like, every piece of code that goes into your every instruction that goes into your algorithm should have a purpose. It should relate to the question at hand. There's no template, right? There's no template for an algorithm. Memorizing a bunch of templates does not make you a programmer, especially if you don't understand what those templates are even doing. So, the whole point of this course, right? The whole way we're teaching programming is we're going to throw you into a bunch of difficult situations, i.e., reasonably hard programming problems, and you are going to be given a set of tools to solve those problems. You are the one who must decide which tools are appropriate in which situation. That's what it means to be a programmer. Like, I think a lot of the criticism that sort of people who don't know how to program very well and have, like, interesting impressions of what it means to program, a lot of these people who, like, come into this class, say things like, oh, he didn't teach us how to program. What they mean is, I didn't, like, give you a program, expect you to memorize it, and then ask you to regurgitate it on the test. Right? That's not how you learn how to program. Not even at the college level, let's say. In order to program, you must be able to work with the building blocks of the programming language, knowing what each of them does, and being able to use them the way that they're intended to be used. You don't just memorize forms, right? That being said, there are a couple of common approaches, right? It's very common when writing a while loop to have a counter variable. It's very common to have an accumulator variable, right? But it's not necessary in all circumstances, right? Not every loop you write will have both of them. Not every loop you have will have, like, some loops may have one but not the other. I don't want you to sort of solidify in your brain, this is the way that loops are written, because that's not the case. Okay? So, good. So here's a question. What does this code output? We've got sum t, I is equal to 0, s is equal to 0, while I is less than the length of t, s plus equals t at I, t being the input, then we return s. T is 5, 10, 15. What is the sum? Ooh, I'm going to do that as a poll. Wait, don't enter it in the chat. I'm going to do it as a poll. Which? A, B, C, D. Ask community. Boing. Three students responding. 4 students responding. 5 students responding. 7 students responding. 'Can you guys see the poll numbers before I close the poll? I'm just curious. Only after you input their answer. Oh, okay. Interesting. Ah, so I can assume then that each one of these is like, you've picked this because that's what you think and not just because everybody picked B. Right? Ah, that's cool. All right. I think that's enough people. I'm going to end the poll. So, yeah, you can't change your answer after you enter it, right? So, 28% of you are correct. All right? The answer to this question is either C or D. And I'll explain why, right? But first, we have to know what the problem is. So, all of you guys who picked B, you missed something about this loop, right? This loop does not modify I, right? So, if we were to actually execute this, I never changes. So I can never fail this comparison. Right? I is always going to be less than the length of t because it's never increasing. So you have 2 possible scenarios here, right? I would say that the more correct answer here is D, because what this is an infinite loop. This loop will literally run forever. It will run forever, and it will never produce an exception, right? So it's not like the program will stop. You know, if I said that it's essentially the same as saying while true. True. Oh my god. Still getting used to this keyboard. While true. Pass. Oh, it's capital. There we go. There. So right now it's trying to execute this loop. Still trying to execute it. That error was one that I produced by canceling the command with my keyboard. That's a keyboard interrupt error, right? However, if I had not interrupted the program, it would still be going. So, it is true that this will never output anything. It is, like, although, okay, this being true, D, I would say, most correct answer. I would still consider C to be a correct answer. An error is when your program doesn't behave as you intend it to. In that sense, the infinite loop which we caused is a type of error, right? So I would say that C is also correct here, right? However, it's not going to produce an exception. It's not going to flash an error message on your screen. So it's a particular type of error, and maybe not the type of error that you thought it would be, right? But it is an error. All right? So, for the 58% of you who missed that, that's okay. That's kind of the whole point of the exercise. For those of you who thought that the answer would be 15, I'm not sure how you got there. Could you also reason that the machine will run out of memory if S becomes too big? In theory, but it would take a very, very long time to do so, and depends on the implementation. Okay. So this is how computer memory works, right? Let's simplify. I'm gonna do a thing. Get it. So rather than adding 5, let's imagine that we're adding 1. All right? Wouldn't it just overflow? Well, it's interesting, actually. In Python, it doesn't overflow because Python will continue to allocate more and more memory to the same integer so long as that integer grows. So in Python, actually, you don't hit overflow, but you would definitely in C. In C, it'll definitely just keep running forever and just keep running inside of the same integer. But yeah. Yes, Richard. Python numbers were theoretically infinite in the sense there is no cap to the numbers and it uses as much memory as it needs. Yes, like integer and Haskell. That's correct, Richard. Yes, absolutely. In C, it would loop back around to being a negative. But so let's just do a little thought experiment, right? Let's imagine we're using 3 bits and we're adding 1, continuously adding 1 in an infinite loop. Right? 0, 1, 1, 1, 0, 0. Right? This is what binary adding looks like, a sequence of binary addition. So there we go. We've run out of room. Add 1 more bit. 1, 0, 0, 0. 1, 0, 0, 1. 1, 0, 1, 0. Dot, dot, dot. 1, 1, 1, 1. So this here takes 8 operations to get here. Right? To get here takes 16 operations, even though I omitted some. Right? Add 1 more bit. It takes 32 operations to get here. Right? Etc., for all the powers of 2. 64, 128, 256, 512, 1024, 248, etc., right? Each bit that you add doubles the amount of, doubles the magnitude of the number you can store. How many bits are there in your memory? Right? If you have, let's just say you have a very, very small computer that only has 1 megabyte of memory available, right? So that's, it's actually technically 2 to the power of, this is a kilobyte, so that's squared, but, let's just say we have 1 kilobyte of memory. Make it easy. So we have 1024 bits available. So we have, well, that would be kilobits then. Multiply it by 8. There you go. That's kilobytes. Right? 2 to the power of that number is the largest number that can be stored inside of this representation. This is extremely large. It might not even be computable in, Google. Let me take a look. google.ca. So we've got 1024 times 8, right? And then 2 to the power of 8192. Infinity. It's big. It's too big. It's not representable. So here's a question. How long does it take to count to infinity? Infinity amount of time. Now, this is obviously not exactly infinity, right? I think that the highest this can do is like, let's see. Yeah. So even at if you had 128 bits available, the highest number you can count is like 3.2 followed by 38 zeros, right? These are big numbers. Very big numbers, right? So basically, like if you were counting, like if you had 128 bits available, right? And you were counting, let's just be generous, 1 billion times a second. You were incrementing that number 1 billion times per second. So we divide that by 10 to the 9. Right? That's how many seconds it would take to fill up only 128 bits, which is that's like 9 bytes. I think that's 9 bytes. Right? So that's the number of seconds. That's the number of minutes. That's the number of hours. That's the number of days. That's the number of years. And, you know, just for interest's sake, age of the universe in years. So far as human beings are able to tell, we have been on the universe has existed for only 13.7 billion years, right? So divide that by 13.7 that would be 9 again. So if the universe were in fact a simulation, right? And you were to pause the universe simulation at this point in time and rerun the whole simulation again, this is the number of times you would have to do that to be able to fill up only 128 bits of data. All right? This is a problem known as the state explosion problem. So it turns out that just slapping a few extra bits onto things, like, that's not going to solve your problem, basically. Make sense? So no, this guy ain't running out anytime soon. It will not eventually run out of it will not eventually run out of data. All right? I know that's kind of a side tangent, but a rather long tangent, but I hope that's useful for you guys. So infinite loops, when you get in one, waiting it out is probably not a great plan, because you'll just, you'll die a very long time before it's finished. So basically, you want to be able to kill the process. On Jupiter, hit the stop button, right? If you're in terminal, Control-C will kill things most of the time. If you're programming on the Jupiter server, right? If you notice that you're in an infinite loop, please kill it as quickly as possible, because you are sharing your server resources with the other students in the class. And infinite loops consume server resources. So, I'm kind of curious. I don't know how many students it would take simultaneously trying to execute infinite loops to bring down the server, but I think it's theoretically possible if enough people were trying to execute infinite loops simultaneously to bring the server down. That would be like a form of DDoS attack. So please don't do that. So, and now for something completely different. Yeah, don't try it out during the exam either. Basically, if the server goes down during a test or exam, you are expected to be able to just, have a local install installed and just flip to it like that. All right, so that's our expectation. So, typecasting. Python implicitly converts between some types. All right, so if you're using integer and floating point operations together, they will coexist harmoniously. However, you can also explicitly convert from one type to another. So, with great power comes great responsibility, guys. Actually, it's kind of interesting. Not to go on another tangent. This summer, I was attending an academic conference. I was attending Theoretical Aspects of Software Engineering, or TASE. It was being held in Cluj-Napoca, which is in Romania, and formerly the capital of Transylvania. So I've been reading Dracula. It's really fun, because I've actually been there, you know. But in this conference, there was one paper that was published, which was, like, describing a type of attack that people use, that's been developed against regular expression engines. Basically, it's an attack that just blows up the complexity of the calculation, so that the server just takes a long time to process your query, and that has the effect of a DDoS attack. You're from there? What? You're from what? Are you from Romania, or are you from Transylvania, or are you from Cluj? Cluj is a beautiful city, by the way. But, you know, in Europe, most cities are beautiful. Europeans don't appreciate how beautiful their cities are, I think. But anyway. So, anyway, typecasting. So, if you have a string that's supposed to represent an integer, you can create an integer from it by using int. Romania, not Transylvania. Yeah, there you go. Cool. Yeah, it's a beautiful country. Absolutely beautiful. You know, an interesting one as well is that you can actually create, you can perform typecasting with data structures as well, which is kind of interesting. So maybe this, yeah, there you go. So if you tupleize a string, you get a tuple of characters, which is kind of interesting. That might be useful, you know, at some point. You can also, like, you know, if you have a tuple 1, 2, 3, 4, 5, you can easily convert it to a list by just doing that. Oh. There you go. And now it's a list. So type conversion is your friend. There we go. So moving right along, let's talk about if statements. So we recall the regular if statement with skipping on the no branch. We recall our if-else construction. We also have this other fancy guy, which is the if-elif-else. Right? So the elif phrase has another condition, but that condition is only ever tested if the first condition comes out false, right? So the order is the order in this diagram. First we test B. If it's true, then S. If not, we test C. If that's true, then T, otherwise U. And you can chain together as many of these as you want, right? You just keep replacing this guy here with another one of these and just nest it infinitely if you want. So, let's write a function that determines whether numbers are even or odd. So you guys remember the modulus operator? If you take any number and you calculate the modulus of it with 2, right? Remember, this is remainder of integer division. If it comes out 0, that means that it evenly divided by 2, which means that it's even. If it doesn't come out, if this comes out as 1, then it's odd, right? Because it did not divide evenly by 2. There was one remainder. And of course, mod 2 is kind of an interesting one because it only has 2 results, right? It will at least when you apply it to integers, it will always either output 0 or 1. So, fine. Let's write a function that determines whether a number is divisible by 5, 2, 5, or 10. So, here we go. What does this program output? So we've got if n mod 2 is equal to 0, return by 2. If n mod 5 is 0, return by 5. If n mod 10 is 0, return by 10. Then print divisibility 5, comma, divisibility 10. What do you guys think? Oh, wait, I'm gonna do the poll. Sorry. Ask my community. You hear that? You guys have been promoted. You're a community now. Good. So it seems that most of you have... Is that is a reference? What? Oh, I'm not aware that was a reference. Sometimes I say things which people on TV have said before I said it. So, you know. Oh, wait. Maybe the show Community? With the comedy show? Where the janitor becomes Napoleon? Or something? Anyway. So, ending the poll now. It seems that the majority of you have come around to the correct answer. Asking for divisibility 5 it'll fail the first condition, but it will pass the second. Right? So the first one is by 5, which is, of course, you have no option but to say that. So what happens with divisibility 10? The first thing that's tested is n mod 2. So what is the remainder of 10 divided by 2? 0. Therefore, we return by 2. The A's have it. There you go. Make sense? Perhaps the thing to understand here is that these are separate calls to the divisibility function. So let's change it the other way. Let's write a function that determines the same thing, but now we've got mod 10, mod 5, mod 2. Let's see what it does this time, huh? Or in this case, I'll just describe it. So in this case, 5 would still fail here because the remainder of 5 divided by 10 is 5, and therefore not 0. The remainder of 5 divided by 5 is 0, so you would get this one for the first one. For divisibility 10, obviously it would hit the first one. So you would get by 5 by 10. Another thing that you might consider doing, you can actually nest these if statements inside of other if statements as well. This is like anytime you have a place where you can write a statement, that statement can be any of the statements we've talked about so far, right? So, n mod 2, so in this case, let's consider divisibility 10. 10 divided by 2, remainder is 0. So we step in here, we test n divided by 10, remainder is 0. So we return by 10. But if we had 6, for example, it would hit the first condition, pass it, step into this if statement, and then return by 2. So there you go. Maybe you should also point out that it wouldn't matter if the elif statements were also if statements because of the return statements. Ah, yeah, thank you, Jeremy. That is a good point. So, I'm not saying this is the most efficient or most, yeah. Well, anyway. So, one particular quirk of this particular example, because these are return statements, right? Anytime execution hits a return statement, it stops the function dead and returns the result and does not execute the rest of the function. So, in essence, it doesn't really matter that these are elifs. It would work just as fine if they were regular if statements. Because if this one's true, right, we execute this. Otherwise, we're going to execute whatever is after the if statement anyways, right? So the exclusivity here doesn't matter, right? Good. So, I'm going to skip Spectre just because it's, we need to keep moving on this stuff. So, linear search. Well, yeah, okay. We'll get into linear search in these last 2 minutes. So, this is our first, what we might consider like a proper algorithm. There's a reason it's called linear search, but you probably won't be able to appreciate that until later on in the course. That's okay. Linear refers to the time complexity of the algorithm, for those of you who know what that means. So, linear search. In linear search, we search through a sequence of values to find the first occurrence of a specified value. It is your basic search operation. For example, locate the first location of a character in a string. We have a function for this, which is index, but how would we implement it ourselves? Let's do it. This is a live coding segment. Beep boop, beep boop, live coding segment. Beep boop, beep boop. They're like, why do you always do this in the last 30 seconds of class? It's like, shush, I'm the prof. So, def, because it's really simple. Lin search. If we have some data structure T, let's imagine it's a tuple, some K that we're looking for. Very simple. I is equal to 0, while I is less than the length of t, don't forget to increment I. If t at I is equal to the thing we're looking for, return I. Otherwise, if that loop iterates right to the end and we haven't returned I, then we know we haven't found it. So we can return false or false. So let's take a look here. Let's say t1 is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. And lin search on t1 looking for element 7. Printf, or just print, not printf. There we go. Ooh. And let's look for something that's not in there. Right? Let's run that code. Ooh. There we go. Python 3. Need to save it. Topic 3. There we go. First, we return 6, which is the index at which this thing is found. 0, 1, 2, 3, 4, 5, 6. And in the second case, we return false. So there we go. Linear search implemented. Cool. Let's see. How did I do? Pretty close. All right. We'll go through the slides implementation. I think it's Tuesday. Tuesday's our first class, I think, yeah? Are there any questions? Could you see the code again? Oh, yeah. Sorry. Sorry, I sometimes get ahead of myself. There we go. The Python operator in is just linear search. Correct. The in operator is just linear search. However, it is also useful to see the implementation, particularly if you're new to programming. Are we going to cover binary search next? Not for a bit, but we will be covering we will be covering binary search. Yes. Are there any faster algorithms than binary search? I think hashing is faster. If you consider hashing a search function, then I believe hashing is faster than binary search. But it depends on what you're searching, right? Okay, well, I'll see you guys next week then. Thank you very much, and I'll talk to you later.